Hi, I am Arjun. In this session, we'll see how to solve the problems related to thermal analysis. And the problem is something like this. A composite slab consists of three materials with thermal conductivities 20 watt per meter degree centigrade, 30 watt per meter degree centigrade, 50 watt per meter degree centigrade, and thickness 0.3 meter, 0.15 meter and 0.15 meter respectively, and the outer surface is exposed to convective heat transfer coefficient of 25 watt per meter square degree centigrade and to a medium at 800 degree centigrade, and we need to determine the temperature distribution within the wall, assume unit cross sectional area, and this is a problem given. Okay, so for this we need to write a finite element structure. So now I'll write finite element structure for this. So we can formulate 4 nodes. We can treat this as T1, T2, T3, T4. Now this will be element 1, slab 2, slab 3. Okay. Now this is this free convention. Now the thermal conductivity matrix. To start with, we will find out the thermal conductivity matrix. Thermal conductivity matrix for 1D heat element is given by, okay, now the thermal conductivity matrix for a 1D heat element is given something like this. So if we consider for element 1, we write K1 is equals to K1 A1 divided by LE1. So LE1 stands for length of the element for 1, plus 1, minus 1, minus 1, plus 1. Now we will substitute values for this. So K1 is 20 watt per meter degree centigrade, so 20, and area is 1 meter square. So length of the element is 0.3 meters. So now I have taken all the values in meter only, all the dimensions in terms of meter only. So minus 1 plus 1, and if we solve this, so the stiffness matrix that will be obtained is 66.66 minus 66.66 minus 66.66 and 66.66. Now this is element stiffness matrix for element 1. This is element 1. And since element 1 is made up of node 1 and node 2, and this can be written as 1, 2, 1, 2. So similarly this is node 3 and this is node 4. So in a similar fashion, now we have to write the conductivity matrix for element 2. Now K2 can be represented as in the same way. K2 can be written as K2 A2 divided by LE2, length of element 2, plus 1, minus 1, minus 1, plus 1. So thermal conductivity for element 2 is 30. So 30 into 1 divided by length is 0.15, plus 1, minus 1, minus 1, plus 1. On simplification, it will be reduced to 200, minus 200, minus 200, plus 200. Now since element 2 is made up of node 2 and 3, you can write 2, 3, 2, 3. So similarly, let us write for element 3. So K3 is equals to K3 A3 divided by LE3, plus 1, minus 1, minus 1, plus 1, 50 into 1 divided by 0.15, plus 1, minus 1, minus 1, plus 1. So this matrix after simplification, So 333.33 minus 333.33 minus 333.33 333.33. Since element 3 is made up of node 3 and 4, so we can write 3, 4, 3, 4. So now we have to write the global stiffness matrix or global conductivity matrix. Global conductivity matrix. So now before writing global conductivity matrix, so at node 1, heat is lost to surroundings. So it is lost to surroundings. At node 1, heat is lost to surroundings by convection, because it is exposed to surroundings. It is exposed, so heat at that end can be written like this, and it can be calculated using this matrix A into H 1 0 0 0. Now area is 1 and heat transfer coefficient H is given as 25 into 1 0 0 0. Now this happens to be 25 0 0 0. Now force vector, let us find out force vector at node 1. Force vector due to free end convection at node 1. At node 1 can be written like this: free end convection so A into H into T infinity. So 1 0, this is the matrix used to find out force vector. So area is 1 and so H is 25, T infinity is 800, 1 into 0. Now after simplification this will become 20,000, 0. So now let us write global thermal conductivity matrix. Global thermal conductivity matrix. Can be written something like this: K is equals to, adding all the three matrices, 66.667 minus 66.667, 0 0, so minus 66.667 to 66.667 minus 200, 0 0 minus 200 minus plus 533.33 minus 333.33, 0 0 minus 333.33 and plus 333.33. Now this is a global thermal conductivity matrix. So now we have to take this and in order to solve this, 66.667 minus 66.667, 0 0 minus 66.667 to 66.667 minus 200, 0, 0, minus 200, 533.33, minus 333.33, 0, 0, minus 333.33, plus 333.33 into the temperatures T1, T2, T3, T4 plus conductivity transfer coefficient values. Just 25, 0, 0, 0, 0, 0, 0, 0, into temperatures T1, T2, T3, T4, and we have to add the force vector. So this is 20,000, 0, 0, 0. Now, so since we have a 4x4 matrix, we need to simplify this. So let us add this value to this matrix. So I'm adding this. So we'll be getting 91.667 minus 66.667, 0, 0. So minus 66.667, 266.667 minus 200, 0, 0, minus 200, 533.33, 533.33 and minus 333.33, 0, 0, minus 333.33 plus 333.33 into the nodal temperatures T1, T2, T3, T4 into, so 20 10 power 3, 0, 0, 0. Now using elimination method and by reducing it to 4x4, so we need to reducing the 4x4 matrix to 3x3. So we'll take this equation. So since we know the temperature T4, so we'll consider the other side of element 3. So we consider this equation and we do a matrix multiplication for this. So 0 into T1, this 0 into T1 minus 200 into T2 minus 200 into this function plus 533 into 33, this into T4. So plus 533.33 into T3 minus 333.33 into T4, since we know the temperature T4. So minus 200 T2 plus 533.33 T3 minus 333.33 into 20 will be equal to 0. And on simplification, now we have to simplify this function. So this will become minus 200 T2 plus 533.33 T3 is equals to 666.66. Now the reduced matrix can be written like this. So 91.667 minus 66.667, 0, minus 66.667, 266.667, minus 200, so 0, minus 200, 533.33. that is what we are doing is, so in this matrix, so we had this matrix, so here what we are doing is, we are simply eliminating this fourth row, fourth column, and we are writing only this, and the value which is obtained here, okay, this value will be added to the force vector. So now we have T1, T2 and T3. So here we had 20 ton per 3, 0. Now this value will get added here. Now by using elimination method, okay, by using elimination method, and if you solve this, if you solve the matrix, so you can obtain value of T1 as 304.76 degrees centigrade, and value of T2 will be 119.04 degrees centigrade, and value of T3 will be 57.14 degrees centigrade, and the nodal temperatures T can be represented like this: 304.76 degree for T1, T2 is 119.04, T3 is 57.14, and T4 is already given degrees centigrade. These are the nodal temperatures. For any clarifications, kindly contact on this number. Thank you.